Okay, what we are going to talk in this video? Actually, there are a couple of things. What problems do LiDAR sensors solve? Why does Elon Musk hates LiDAR? How LiDAR actually works and collects the data? And another important thing, and maybe the most exciting, how to create a map using LiDAR data and store it so that a robot can use it later.
Hi guys, so I'm back after a long time. In this video, I'm going to talk about LiDARs. If you don't know, I'm a bit into robotics. So LiDARs, they're really beautiful things, very useful things in robotics actually. So let's start with the problem, right? LiDAR is a solution, but what's the actual problem? Due to which we are inclining towards LiDAR to solve those problems in robotics. So LiDARs. Okay, let's suppose that there is an autonomous vehicle, a car. A car is a very good example, and it's popular as well. The We all know the self-driving vehicles from Tesla, right? So what's the fuss about that? Fuss actually is they can actually autonomously map the environment and locate themselves in that environment and navigate through that environment to take useful decisions. For a self-driving car, the decision would be to either to drive, either to continue driving, either to speed up, or to stop in front of red traffic signals, or if there is a pedestrian in the road, you gotta stop. So that's a meaningful decision that a robot can take. A self-driving car, Tesla car, it's a robot. But actually, Tesla does not use LiDAR. It uses camera. Elon Musk doesn't like LiDARs, guys. He doesn't like LiDARs because he thinks it's foolish to use them. But is it really? So let's suppose we have a little robot, and the application of that robot is to navigate through a small, simple environment. So I'm going to show you an example, right? I'm gonna I'm going to open a software that's Weebot, and there I have actually I've actually simulated the environment for a robot, and I'm going to show you how actually lidars work. Okay, okay, Weebot is already open. All right, can you see? Can you see the world? Can you see the world, guys? Yeah. So actually this robot right here, as you can see, right, this is the robot, little epoch robot. You can see it can, if you allow, it can move around this arena. We call it arena. Let's say a robot is in such an environment, right? And currently the robot is programmed to actually follow this line. So let's see the demo so that you actually understand what's going on. So as the robot moves around this line, it's going to create a map in this window. So we programmed it using Python, right? And there are a bunch of different objects in the environment. So as I play the simulation, you can see for yourself. Look at that. So these rays that you are seeing are actually the rays of LiDAR sensor. And when it hits any obstacle, what it gives is the angle at which it is getting that obstacle data, and the point is actually a point that much far away from the sensor actually. So if you look at this, the robot is able to follow the line, it knows where it is. So for its position, it is creating a line, and for the position of obstacles, it is creating these obstacles in red color, as you can see. So how is it able to do that? It is due to the LiDAR sensors. So imagine an autonomous vehicle in a similar situation would know where it is in the map, and it has understanding of the obstacles that is in its way. Look at this duck. So it's projecting its rays to everything around it. So the field of view of this lidar sensor actually is 360 degrees. That's why it can see all its surrounding. And there is something called the frequency at which the data is being achieved. So every time the lidar, it spits out an array of 360 values, and those values correspond to the obstacle distance at each degree, right? So for 1 degree there is 1 point. So going through that full circle, you get 360 points. So as you can see, it is clear. It is carefully mapping out the environment. So it has already understood how the environment it looks like. Again, okay, I'm going to zoom in that a little bit. So you can see it's not accurate, right? Because there is noise in sensor data as well, right? The noise in sensor is not making it able to accurately predict. But look at this. I think this is a very good map. So I had actually put a little can, soda can, in the corner, and look at this. It is able to map that out as well. But in reality, is the LiDAR sensor so accurate? Maybe or may not be. So it depends on various parameters or specifications of the LiDAR as well. But LiDAR itself, if it provides 360-degree field of view and obstacles, so okay, let's talk about it. So as you can see, the in this software we can see actually the 0 degree of the LiDAR. So for LiDAR this way, as you can see, it's 0 degree. So in this direction it's 0 degree, and from that every other ray is 1 degrees apart. Okay, so as you can see, this is a nice little robot, and the LiDAR sensor is above that robot, and it is projecting rays, and through its internal sensory mechanism, there are different mechanisms to read the values of its surroundings. But let's talk a bit more technical things about it. So how do you transfer, right, the sensors, the data that we receive as an array of 360 degrees, and turn it into a nice graph where the robot can localize itself, and it's mapping out the environment correctly, and it even drew this line because it was already following the line. So this gives us a good approximation of how efficiently it is localizing itself. But there is a trick. For the localization, what ideas do you guys have? For localization, we're actually using the encoders in the robot wheels, right? And there is some for kinematics to derive the changes in position and velocity, sorry, position and orientation of the robot according to the wheel velocity. So if you look at this, this is a differential drive robot. What does that mean? A differential drive robot means it can move forward using its two wheels, given both wheels are running at constant velocity. But what happens if one wheel is running slower and another is running faster? So that will make the robot turn towards the direction of the wheel which is running slower, right? So that's the differential drive robot. Now we need to take the velocity, instantaneous velocities of this wheel at each time step, and we need to convert that velocity into the change in position and orientation of the robot. One thing really interesting is, let me turn on the coordinate frame of this robot. So blue is Z, green is Y, and red is X, right? So in the X direction, robot can move always in X direction of the robot frame. So if you look at the things in with respect to the robot frame, the robot cannot do much because it can only move forward in X direction of the robot frame. It cannot move towards Y direction, right? It cannot go towards this green direction, because if I let's say if I rotate this, right? Okay, if I rotate this robot, what happens is not only the robot sorry, I rotated the LiDAR actually. Okay, okay, okay. I turned the robot little left, little towards right, right? But what happens is it still cannot go towards towards the x-axis of itself, because you see, because the robot is moving only in its own coordinate frame, right? Sorry, oh my god. I actually the turned the children. Okay, let me do that. Okay, so -1. Sorry. I think you get the point, right? Even if I rotate the robot according to its own reference frame, in robot coordinate frame, the robot can only move towards forward. It cannot go sideways, right? It can only move towards the red axis, front. But there is another motion, or there is another motion that the robot can perform, and that is rotation about this blue z axis, right? you can turn on this plane. So how does the robot achieve that? It achieves that by actually, as I already said, changing or having different speeds in different wheels. So we measure the velocity of the wheels and convert that to the either the change in forward direction or rotation about the z-axis, right? Robot can rotate around the z-axis. So there are only two changes in the robot's position in its own frame, right? Del x, and we call it omega z, the velocity towards the front, and the rotating velocity or angular velocity about its own vertical axis. So how do we, uh, okay, given that we know the initial position, let's say we know the initial position the robot is at, right? So we can create a transformation matrix that maps the position of the robot or the alterations in the position and orientation of the robot in its own robot frame to the world frame. So world frame is this, and for convenience, we have put this robot at origin of the world frame. But as you can see, there is still a rotation element. So the robot is turning clockwise, counterclockwise, positive 90 degrees about z-axis already, according with respect to the world frame. So we can map these things, right? I don't want to go to the code right now. So that's the transformation that takes the increments in direct position. So increments in this direct position and increments in omega z to actually track the change in position of the robot throughout its journey along the line. So that gives us how we can do localization. Okay, the problem of localization is then solved. We don't need LiDARs right now. With the velocity sensors in wheels of the robot, we can localize it. But to what degree of accuracy, that's always doubtful. Okay, let me run this simulation again as I explained you. So the problem of localization we have already solved is using the velocity of the wheels to determine where it is right now based on a reference position at which the robot started. So the next problem now is the mapping of the environment. Okay, the robot knows where it is right now. How to make the robot know what is around itself in the environment. That problem can be solved using the LiDAR sensor. The LiDAR sensor, in some way, can get data all around itself. That means we can we can convert that radial data, right? It gives us the radius. All right, the radius might be changing at different angles because there may be obstacles. So imagine a circle, right? Let me draw it on my paper and show you. Okay, so the center point is the center of the LiDAR sensor, and these are the rays that are coming out, right? These are the rays, and there are 360 rays that are going around in the sensor. So let's say we know, and there are obstacles, right? So if there is no obstacle, it goes full on, right? It goes as far as it can. But let's say if there is an obstacle around here, so if we take it at 0 degrees, at about negative 45 degrees, what you're gonna get is a point, and that is the distance r. So are you getting it? How do we get the values from the LiDAR? So we get this r, and that r depends on where the obstacle is. So at 90 degrees, the point, the r1, I will say, r1 will be different. So we get 360 different values around the circle that correspond to the distance from the center of the sensor to the obstacle. So after we have that, the old trigonometry trick, right? X equals r cos theta, y equals r sin theta. So this is the old trigonometry trick that we've been using in various mathematics classes. So using this trick, we can easily determine the x and y position of the obstacle or that point, right? X and y position of that point relative to the robot coordinate frame. So after having an x and y position in robot coordinate frame, we already have the transformation matrix that maps the robot coordinate frame to the world coordinate frame. If we know where the robot is with respect to the world, we can know where the point is in that world given by the robot or the LiDAR sensor. So that's how we solve the problem of mapping an environment. Look at this. So how do we convert that X and Y into this map? It's simple. This display is just a 300 by 300 pixels array. So we create an array and we fill up the values in an array either to light up that array with red color or not based on the points detected by the LiDAR sensor. Suppose the point detected by LiDAR sensor is in 0.5 meter in x direction and 1 meters in y direction. So that will represent somewhere along this wall. So for that point, how do we map that point in our display to this point? So we need another mapping function. I'm not going to code in this video. I think that's all for this video. It was about how LiDARs work and how the data from the LiDAR can be transformed into such a map, which beautifully represents the map of the environment that the robot is moving moving through, right? That was all for this video. I will follow up more on this video by actually walking through the programming aspects and the coordinate frame transformation. I'm not talking much about it, but this is just to give you a kick, right? To give you a kick of passion that will ignite you to further investigate on this technology. Thank you.